Thanks for the introduction. This is joint work with Alan Cheng, Jaume de Dios Pont, Rachel Greenfeld, Asghar Jamnishan, and Jose Madrid. Most of us all used to be at UCLA, and then we've gone to other places. This is why we have some different affiliations now. Okay, so let's first talk about some number theoretic motivation. So here we're going to fix a base B, and we're going to fix a subset A of 0 to B minus 1. So if you don't like sub-abstractness, take B to be 10. A is a subset of 0 to 9. Okay, and we're going to define curly E to be called an ellipse-suffix set, and it'll be defined to be the collection of integers when written in base B have digits in A. Okay, and these are sort of, it's good to think that these are sort of arithmetic analogs of a Cantor set. And so let's ask the following number theory question. So I give you two equations and two S variables. So N1 to N2S, all of these integers, and these are all integers. And ask, well, how many solutions are these to, how many 2S tuples are there such that they satisfy this equation and they lie between 1 and N, and when written in base B, they have digits in A. Okay. So if A is the full collection of digits, well, then my ellipse-suffix set is just all the integers. Okay, and this is just essentially reduces, well, this is literally the quadratic case of Winograda's mean value theorem, which was solved. But what if I take A to be a strict subset? And I'm actually going to take A to not just be a singleton. I'm going to take A to be slightly more than, at least have 2 digits. This particular problem, when A was a strict subset, was studied by Kirsty Biggs using the method of efficient congruencing for certain A and sort of asymptotically in B. So there are some conditions on B and A that she solves this for that I don't want to go into at this point. And so the motivation of this talk is to understand and interpret Biggs's efficient congruencing argument in terms of decoupling. So the broader picture is that in 2015 and in around those times, there were two proofs of Winograda's mean value theorem. One was an efficient congruencing proof, a number theory proof, and another was a harmonic analysis proof by Bourgain, Demeter, and Guth. And recently, in the last few years, there have been studies about how these proofs are related. So this is another attempt at studying how does the efficient congruencing argument, how should I interpret this into decoupling language? Okay, so let's make our life easy. And instead of studying the linear and quadratic equation, let's just study the linear equation. And let's also maybe pick S to be small. Let's pick S to be 2. Okay, so we're now down to the linear equation and 4 variables. That's great. Okay, now let's even be more concrete and let's pick our ellipse-suffix set. Let's pick our base and our strict subset of digits that we restrict to. So I'm going to take, for concreteness, I'm going to take our base to be 10, our subset to be 0, 1, 2. And our ellipse-suffix set is the set of non-negative integers with only digits 0, 1, and 2. And I don't want to say this over and over, so we're going to refer to this set as 0, 1, 2 base 10. Okay? And so EJ will be the set of integers between 0 and 10 to the j containing only digits 0, 1, and 2. And in other words, EJ, how should we think of EJ? EJ are the j-digit numbers containing only digits 0, 1, and 2. And by j-digits, I mean, I say 0, 0, 0 is a 3-digit number. Okay? Okay, so our question, then let's play with the toy problem. We ask how many 4 tuples, N1 to N4, are there such that N1 plus N2 is N3 plus N4, and these Ni's are all j-digit numbers containing only 0, 1, and 2. Okay, so let's even make the problem easier. Let's even specify j. Okay, so let's pick j equals 1. Okay, what is this problem now? So we want to count solutions. So N1 plus N2 is N3 plus N4, where the Ni's are 1-digit numbers where all the digits are 0, 1, and 2. So literally, and each of the Ni's are 0, 1, and 2. So this is a finite problem, right? I mean, there are 3 to the 4 many possible choices. Just list them or iterate them all. And you go through them and you find that there are 19 such 4 tuples. Okay, and unique 4 tuples. Okay, great. So that's great. So we solved the easiest sub problem we can find. Okay, so let's upgrade. Let's find the next hard problem. Let's do j equals 2. Okay, so we want to count the number of solutions to this system right here, where the Ni's are 2-digit numbers, where 0, 0 is a 2-digit number. There are 2-digit numbers where each digit is 0, 1, and 2. Great, so on one hand, how many do I have? I have 9 9 digits here. This is also a finite problem. I could iterate through 9 to the 4 many. Sure, a computer can do that. But let's be a bit more clever. So let's imagine, so n1, and I just want to add n2. So I'm going to write n1 as a1, b1, where a1 and b1 are digits, n2 as a2, b2 and their digits. And we're going to add just like in elementary school. Okay, so one special property is that this situation has no carryover. So b1, b2 are the digits 0, 1, and 2. So when I add, let's say b1 might be 1 and b2 might be 2. Well, I add 1 plus 2, I write a 3 here, and I don't carry over anything. So, and similarly, a1 and a2 are the same thing. There's no carryover. And this is compared to the situation if I'm adding like 65 plus 75, I have to carry a 1, right? So in this special situation, because of my Cantor set, my elliptic set has a nice structure, there is no carryover. And what happens is that this problem then becomes a tensor product of the problem digit-wise. And I know in each digit how to solve, how to count solutions where my digits lie between 0, 1, and 2. And there are 19 many solutions per digit. And so since I have 2 digits, there are 19 squared many solutions. Okay, so here, of course, then in general, there are 19 to j many solutions because we're in the situation of no carryover and the problem reduces to each digit. Okay, so in our paper, we consider some certain carryover cases, but not all of them because the combinatorics become a bit complicated, but we're not going to discuss that this time. Okay, so let's start generalizing the problem. Okay, so I'm going to let aj be the best constant that I can put here for all sequences an. So what is this inequality? This inequality says I have this exponential sum. I'm indexed. This exponential sum is indexed by the elliptic integers. These are indexed by the integers that are 0, 1, 2, base 10, and they have j digits. Okay, and I ask, basically aj measures how much does it cost to force square root cancellation to happen on the left-hand side. Okay, and aj is the best constant to put there. Okay, so put it another way, aj is the maximum of this guy subject to the fact that the right-hand side equals 1. Okay, so we know how to compute at least one special case of the left-hand side. It's the case when aj equals 1. Okay, if we compute aj equals 1, then if I put a 1 here, okay, that's an L4 norm. So what do you do with an L4 norm? You expand everything, okay, and then you interchange the integral and the sum, and then now you have an e to the 2 pi I. So if you use the identity that 0 to 1 of e to the 2 pi I n x dx, this is the indicator function of n being 0, you observe that the left-hand side, when I put an equals 1, counts exactly the number of solutions to this equation where the ni live in ej. And I actually know how many there are. There are 19 to the j many solutions. So I have this guy, and I want to relate this 19 to the j somehow to give me some information about aj. So I have to make this term appear with the an equal 1. So I do that. And then therefore I'm left with a 19 over 9 to the j. Okay, so that's some arithmetic. And so since aj is the soup, okay, and I've exhibited one such example, aj to the 4 is at least 19 over 9 to the j. And then we can ask, is this best possible? So usually in this game, in discrete restriction, we'd like to think that aj equals 1 is the optimizer, but it turns out to be not true. So we can play again. We can play again this game where what happens when j equals 1? Well, when j equals 1, okay, we're just having one digit numbers with digits 0, 1, and 2. And our goal is to maximize this expression subject to the sum of the squares, coefficients being 1. So, okay, so this L4 norm, we expand, it's a quadratic form. So we want to maximize this quadratic expression subject to this quadratic constraint. And this is exactly what, Calc 3 is built for. So you do that and you compute that the maximum is 15 over 7. And a strange thing happens in that the coefficients that exhibit this optimum is not constant, which is a bit different from the behavior we expect in normal discrete restriction. Okay, so one can immediately compute that 15 over 7 is bigger than 19 over 9. Great. So what? Maybe this is a fluke. So if you do it once again for j equals 2, okay, I want to maximize. So these are the 2-digit numbers with digits 0, 1, and 2. And I want to maximize this quadratic equation subject to this constraint. And once again, you can go through the motions of of doing, this sort of basic calculus exercise, and you compute, so the maximum is 225 over 49, which is 15 over 7 squared. And well, this is the maximum, this is A1 squared, right? And once again, you see, and with some work, you can show that, I probably should put a 4 here, and you can write down the maximizer, and then there's some relationship between the maximizer of the A2 case and the A1 case. And essentially, this tensor product observation that we observed at the beginning of the talk carries over, in that because we're in the no carryover case, the problem tensorizes into just digit by digit constraints. And so the general case will just be the single digit case raised to the jth power, to however many digits we have. And you can show that in general, indeed, the discrete restriction constant is 15 over 7 to the j, which is bigger than what we would expect if we just pick n equals 1. So the optimizers are not constant, which is surprising, at least for us. So I've talked a lot about discrete restriction on number theory. Where's the harmonic analysis? So let's go to the harmonic analysis. My tablet would let me. Okay. Okay, so let's now start talking about harmonic analysis. I have to thank Tongo for setting up decoupling for me. Okay, so first let's make solid the connection between ellipsephic integers and Cantor sets. Okay, so to talk about this, let's now think about the standard Cantor set and its associated ellipsephic integers. So here, and for only this slide, E will be the set of integers when written in base 3 have digits 0 and 2. And let's consider EJ. So EJ is the collection of integers when written in base 3 have only j digits, and each digit is 0 or 2. Okay, I claim that this corresponds to the jth level of the standard Cantor set. And indeed, you can work this out and write it out this way. But I like to remember it this way. So how do we construct the standard Cantor set? Here's the interval 0, 1. And the first level is basically saying intervals of length 1/3. And the second level, I take middle thirds of everything like that. Okay, and to each interval, I'm just going to write a 0 and 2 on top. 0, 2, 0, 2, 0, 2. Okay, so what's this interval? This interval is associated to 0, 2, 2. And then what's this interval? This associated is to 2, 2, 0, base 3. Okay, and then once you write it down, you'll properly see that this definition is correct. Now, maybe there's an off by 1 index, but essentially it's how you think of it. Okay, this is how ellipsephic integers have a 1-to-1 correspondence with parts of the Cantor set. Okay, so, and the trivial ellipsephic set, it's the collection of integers when written in base 3 have digits 0, 1, and 2. Well, that's all the integers. This corresponds to a partition of 0, 1 into intervals of length 3 to the minus 3. Okay, so that's how ellipsephic sets involve Cantor sets. And now let's talk about decoupling for Cantor sets. Okay, so here we've already defined AJ. AJ is the best constant that I can put in this inequality. In other words, AJ is the best constant that I can put here. So I have how much does it cost to have square root cancellation? Okay, so now let's define decoupling for a subset of the line. Okay, so given an interval I, I'm going to let fi be defined to be on the Fourier side as such. Okay, it's just fi hat is f hat indicator function of I. And kj is the best constant such that I can put here. So what is this? How should we think of this? So I have a Cantor set on the line. So here's my 0, 1. And I have some sort of level of a Cantor set. Okay, maybe I let my Cantor set develop and pause time. And it looks like this. And then I ask, what is kj? So let's imagine we have a function that's Fourier supported on all these green pieces. This Fourier transform is supported on the green pieces. And I want to measure it in L4. Kj measures how much does it cost to break up the L4 norm of the function that's supported on all these pieces. How much does it cost to break up into the L4 norm of each of its individual piece? Okay, so Kj sort of measures how much does it cost to sort of, it measures sort of how orthogonal is the function on each of these individual pieces in Fourier transform. Okay, and somewhat surprisingly, so usually how this theory works is that this is a function, this estimate is more general. This is a number theory estimate. If I pick a function that's just a sum of Dirac deltas, then I get this estimate because this is a weaker estimate than this. So usually this implication is obvious. Now, what's surprising, because we're working on the line, actually, if it's enough to actually know this estimate is already strong enough to imply this estimate, mostly because of the one-to-one correspondence between the LF suffix set and the Cantor set. So this is the most surprising part, in that knowing the number theory can imply the analysis. Usually it goes the other way. So in this case, in decoupling for the line, these problems are equivalent. So I would prove that if I had more time, but I encourage, if you're interested, we write it out in a lot of detail in our paper. So what does that mean for us? Well, so we spent a lot of effort considering the 0, 1, 2 base 10 LF suffix set. And we showed that, well, to force square root cancellation in this exponential sum over here, we must lose the best constant we can put here, so that this is true for all an, is 15 over 7 to the j. And the fact that this discrete restriction problem is equivalent to the decoupling problem, it turns out the best constant we can put here is also 15 over 7 to the j. And this is also best possible. Because if there was a better example, then that means there's a better example here. Right? And so, okay, so more or less in this case, we understand the decoupling problem for the line. And now the idea is that we want to upgrade to decoupling for the parabola, because we know the one dimension, so let's move up to another dimension, the parabola. Okay, so what's the problem over there? Okay, so now to each Cantor set, we sort of have a natural scale. So for example, we take the jth generation of the Cantor set, the standard Cantor set, the natural scale is 3 to the minus j, since that's how big our intervals are. Okay, so let's imagine we had we have a level. Okay, so here's our Cantor set. We know it looks like this, and then let's lift it to the parabola, and on the parabola it looks like this. Okay, so now we're going to form these little pieces, just like Tongo talked about, where if these are a length delta of j, these pieces are a thickened delta of j squared. We choose this scale so that this is the scale for which we have roughly flatness. We sort of can ignore the curvature locally. Okay, and we call these pieces theta I, if I is the interval down below. And f theta I is defined once again on the Fourier side to be Fourier restriction to 1 theta I. And dp of delta j is the best constant such that this inequality is true. Now, what does this measure? Well, this measures the fact that if I had a function that's Fourier transform on all these green boxes, how much does it cost to break up the LP norm of this function into the LP norm of each of its individual pieces? And how do I measure my cost? I measure it in little L2. Okay? So dp delta measures how much does it cost to break up the LP norm of the sum into the sum of the LP norms for all functions f whose Fourier transform is supported here. So what are we asking? We're at dp of delta asks for how much does it cost to decouple a function whose Fourier transform is supported on a pretty sparse subset of the parabola. There's a lot of emptiness. Okay, so I've rewritten the inequality here. And so if my Cantor set is 0, 1, okay, that we had a trivial LF suffix set, which corresponds to just a partition of 0, 1 into just intervals of length 3 to the minus j. Then this decoupling constant is just the same decoupling constant studied by Bourgain and Demeter. But we have sparseness. So for sparse subsets of the parabola, actually the Bourgain-Demeter bound can be worse than trivial. So for example, if Cj is the Cantor set that corresponds to the 0, 1, 2 base 10, then the number of intervals on each level we have is 3 to the j. We have 3 to the j many intervals at each level. And each interval at each level, each interval is length 10 to the minus j. So trivially, by Cauchy-Schwarz, you know that, let's say, the L2, L12 decoupling constant, if we had 12 here, is bounded by the number of intervals to the 1/2, which is this guy. And if you apply Bourgain and Demeter, okay, just directly apply it, you get something even worse than trivial. You get 1.78 to the j. Great. And it's because the number of intervals is much, much smaller than the sort of inverse scale we have. 3 to the j is much, much smaller than 10 to the j. And this is why the trivial bound is even better than Bourgain and Demeter. And so
you have a couple of minutes left.
Yep, this is my last slide. So our main theorem is that, well, how do you measure? So our main theorem says the following. We have a Cantor set on the parabola. And we want to, let's say, let's restrict to p equals 4. Okay, so let's take 3p to be 12. So let's say I want to measure the L2, L12 decoupling of these blue sets on the parabola. Where our theorem says that, well, to measure how big this is, it suffices to measure how much does it cost to decouple the projection of the blue set on the line. And if I know how much this costs, then I can upgrade it onto the parabola and it just doesn't cost any much more. Okay, so in this context, if Cj is the Cantor set associated to 0, 1, 2, base 10, we know from the previous slide that it costs 15 over 7 to the j over 4, divided by 4, to decouple on the line. No, I can't click. Okay, so this theorem says that, well, how much does it cost to decouple the L2, L12 guy on the parabola? Well, it doesn't cost much more than how much it costs on the line. And this is about 1.21, which is much better than the trivial bound and the bound of Borgan-Demeter of 1.7 and so on and so forth. However, the downside of our approach is we're not actually certain if this lifting process or you can say the projecting process from the parabola, reducing the problem from the parabola to the line is sharp, but we certainly get much better bounds than what is currently known. We're basically using the sparsity. And furthermore, if you restrict to the case where we have the trivial Cantor set, this is actually a generalization of the Borgan-Demeter decoupling theorem, mostly because they resort to using basically Plancherel, so p equals 2. If p equals 2 here, then we get 6 here, and then we recover the regular Borgan-Demeter parabola decoupling theorem. And that's all I have. So thanks for listening.